Okay, so this is the outline of chapter 23 about the Gauss law. So this is the outline. So first we'll introduce a new variable called electric flux, and then we'll talk about the main topic here, the Gauss law, and then we'll also introduce the charge isolated conductor, and then apply the Gauss law to some symmetrical structure like cylindrical symmetry, planar symmetry, spherical symmetry, so that in some sort of symmetrical structure we can simplify the Gaussian integral just by simple multiplication. Okay, so it will simplify the calculation, but the problem is you need to understand some of the more complicated mathematics, like surface integral or what it means. Okay, and then you can apply it to skip over some complicated integration. Okay, so this is an overview of the electromagnetism. Okay, as you know, this semester we mainly learn about the electromagnetism. So if you would like to summarize electromagnetism in 2 words, we'll say it is a Maxwell equation. Okay, so actually Maxwell equation includes 4 laws. So the first one will be Gauss law here, actually the third line here. So in this chapter we will actually learn about the Gauss law, although in this textbook or in the slides we will not actually using this notation. Here it is using D, but actually we're using something like this. Okay, actually the notation is different, but the content is the same, so I just use this figure here. So actually in this chapter we'll learn the Gauss law, and later in this semester we will also learn Ampere's law in chapter 29, Faraday's law in chapter 30, and this is another Gauss law for the B field. Okay, the B field version of the Gauss law, and actually you can see on the left side they are similar. So this is a surface integral, a closed surface integral of D, and then this is a closed surface integral of B. And on the right side, this is actually the total charge in inside the Gaussian surface, and actually there is 0 on the right side of the Gauss law of the B field. Okay, so later on we will know what it really means, but generally here I'd like to let you know this is an overview of the electromagnetism. Okay, so inside the Maxwell equation we have 4 laws. Okay, actually we can solve many problems related to the electromagnetism. Okay, so first of all we will introduce a concept called electric flux. Electric flux 这个叫做flux 叫做通量嘛。对，那 okay, so here it says Gauss law relates the electric field at points on a closed 这是一个封闭的 closed Gaussian surface， 就是高斯面了。To the net charge enclosed by that surface. Okay, so so here we can see there are 3 figures here. So let it see it one by one. So on the left side, suppose we have a charge. Okay, we have a charge here. Okay, we have also a charge, but this one is yes, actually it's large. No. So actually you can see that here is a charge, and suppose it is a positive charge, and then with a charge amount plus Q, and of course it will generate some E field in the in the whole space. So, and actually you know that E will be K times Q over R squared. R is the distance from this charge to the point we concern. Okay, for example, here, then R will be this one, and then suppose this point is here, and R will be that one. Okay, so we have learned it in the previous chapter, so there should be no problem here. And the idea here is that in the previous chapter, we also know that there is something called the electric field line, right? Electric field line. Yeah. So actually, yeah. So this positive charge, yeah, this is plus Q, will generate some E field pointing outwards. Okay. And here, what we would like to do is we try to draw a circle, or actually a sphere, which is in 3D, a sphere, S-P-H-E-R-E， 就是画一个球体，但这个是一个平面，所以你只看到一个圆形。Okay, so actually we try to draw a sphere here. Actually, this sphere is not physically exists; it's just an imaginary shape. OK， 它是想象出来的，它不是一个实体有一个球在那边，它只是一个幻想出来的一个球面。OK， so here we will try to observe how many E field lines go through this sphere. Okay, so for example, in this figure, we can see there is 1, 2, 3, 4, 5, 6, 7, 8. There are totally 8 electric field lines going through this circle. This circle, of course, in the 3D figure, it is not possible to really count, but yeah, actually in 2D we can really count. There are 8 arrows going through. And here, for the second one, suppose we have a larger charge as positive 2Q. Okay, so yeah, actually I just like to equalize the figure. So actually you can imagine, yeah, these two circles are having the same size. So actually, when we try to count how many E field lines going through this circle, we can actually count. There should be totally 16. There are 8 electric field line going through, and here we should have 16 electric field lines going through. Okay, so as much as the charge is 2 times larger, that should be 2 times the electric field line going through. Okay, and actually it's according to the assumption for the electric field line, which means that if the E field is stronger in magnitude, then the E field line should be denser. 支线会比较密的。Okay, so in such a way we have more lines going through this imaginary circle. And actually here we have negative 0.5 Q here, negative 0.5 Q here. So negative 1/2 Q. Okay, so the magnitude of the charge is smaller, and also the polarity is negative. So which means it will generate some E field pointing towards this charge. And in such a way, yeah, we can actually count there are 4 E field lines going through this circle. And one difference is that as much as these two charges are positive, then the E field line will be going outside, going outward. And in this case, this charge is negative. So the E field line will be pointing inward. Okay. So here we have some idea that we don't actually need to know. And actually, I mean, suppose if we can really observe how many E field lines going through certain area or certain surface. We can see whether the total E field is going inside or outside. We'll know the charge amount inside this closed surface. And also we can see the magnitude of the total E field. It is strange, but yeah, so it is actually called the flux, not the total E field. Yeah, actually we'll see. Actually, when we count the total flux going through the Gauss, the closed surface, and then we will see how large the charge is. Okay, we have some kind of observation like this. Okay, so here we come to a more rigorous definition for the electric flux. Okay, so here we have actually we have a formula like this. Okay, so this is d phi is the electric flux, and d means the phi in a small area. Okay, so it equals to the E field dotted with dA. Okay, so let's see what is dA. Okay, so here it says area vector dA for an area element, patch element on a surface is a vector. OK， 所以这个是一个叫做面积向量，那面积向量当然是一个向量。那当我们讲一个向量的话，我们最简单定义它的话，就是我们要知道它的方向跟大小嘛。OK， so here it says that is perpendicular to the element， 就是跟这个 element， 就比如说现在我们这个 this is the element， this is the element。Okay, and then we try to define the area vector for this element. Okay, so when we consider the area vector, okay, so the area vector has a direction which is perpendicular to the element, okay, which means that the dA should be parallel to this axis. Okay, so actually there will be two possibilities. One of the possibilities is that dA is pointing to the left side or dA is pointing to the right side. Okay, so actually if it is not a closed surface, then this dA is free for you to define. Okay, 如果不是一个封闭的面的话，那这个 dA 的方向有两种可能，可以左可以右。那你可以自己定义的，但你要记得定义了左边还是右边，不要你算定义了左边，然后算一算你当成右边，然后就会出现一些正负号的问题但是它是可以让你自己定义的。So the only constraint is that this dA is perpendicular to the element. Okay, so maybe this is a curvature. So 它如果是一个曲面，那就是一个切面。跟那个切面垂直，OK。但是这里另外一种想法的话，就是当我们把这个曲面切成很小一块的时候，那我们就可以当做那小块是一个平面，就是这个意思。那我们就是这个 dA 就是跟它垂直就好。OK，and has a magnitude equal to the area。那大小的话就是这个小块的面积，所以我们就有那个面积跟方向。Okay, so and then electric flux defined through a patch element with the area vector dA is given by a dot product. Okay, 所以这个 electric flux是一个 scalar 是一个纯量。Okay, so d phi equals to E dot dA. So dot is this is the dot product. Okay, and actually when we would like to calculate this stuff, we can imagine this d phi or delta phi is similar thing. We just change d to delta only. So yeah, just some notation, but actually they are the same thing. So you can imagine when we would like to calculate this stuff, you can consider like d phi equals e dA cosine of theta. So which means that the dot product is like the product of the magnitude of the two vectors, and then multiply cosine of theta, where theta is the angle between the two vectors you need to dot. Okay, so in this figure we try to consider dA is actually pointing to the right side. So in such a way, E and dA can be dotted, two vectors can be dotted to be a scalar. So it is like E, the magnitude of E times the magnitude of dA, and then times cosine of theta. Theta is the angle between E and dA. Okay. Yeah. Okay, so here we actually try to define something called the total flux and net flux. Okay, so the total flux through a surface is given by this surface integral. Okay, this surface integral. 这个就是 total flux。那它定义给一个就是任意的面都可以定义的，那就是 total flux。那就是把刚才很多的这种 d phi 等于1到 dA， 本来是一个很大的面，甚至是一个大的曲面，那我们切成很多小块，每个小块我们可以算这个 dot product。那最后我们把它加起来就是一个积分，那就写成这样。Okay, so this like the total flux is like the sum of many small flux through the small patches, and then we try to add them together using the integral, so that it can be written as a surface integral like this. The phi equals integration of E dot dA. And then the SI unit for the phi will be this one. Okay, so if you still remember, okay, the SI unit for E, it will be N over C, and then this is the area vector, so the SI unit will be M squared. So the overall SI unit will be M squared over C, or something like this. And here we also try to define a variable called net flux, 就是一个净的通量。Okay, so actually this one only defines for a closed surface, closed surface 就是封闭的曲面。Okay, so the only difference is that we have a circle here. Okay, so this circle means you do an integration for a closed surface because this is an area vector. So which means that actually this integration is two-dimensional. Okay, so actually it is for a closed surface. Okay, so it will be written like this. So you don't need to be afraid of this notation. This just a notation. So this circle only means you do the integration for a closed surface here. Okay, and so here we have a note. The note, it says if phi is greater than 0, then we will say the net flux is going outward. It's going outward. And then if phi is less than 0, we will say the flux is inward. Okay, so here we would like to emphasize that, okay, for a Gaussian surface, or we can call it a closed surface. So usually this textbook calls Gaussian surface, but actually it means closed surface. So for a closed surface, when we try to define the dA for each patch. So just now I mentioned that dA can be point to either direction. But here for closed surface, the dA always pointing outward. Always pointing outward. dA always points outward. So this is the rule we must follow. Okay, so in such a way, if we have E dot dA and then do the integration is greater than 0, which means that this E field is actually going outward. Maybe some are positive, some are negative, but the total sum, if the total sum is positive, which means that the part that going outside is more than the part that is going inside. And then in this way, it is generally, the E field is generally going outward. And on the other hand, if phi is negative, which means that if all the E field is going out inside, or most of the E field going inside, and a little bit of the E field going outside, then the overall sum will be a negative value. Then we will say the E field is generally going inward. Okay, so this is a boundary to cut it out. Phi is 0, then there's no flux. And if phi is 0, phi is larger than 0, then the E field is going outward. And if phi is smaller than 0, then the E field is going inward. Okay, so far any questions? Yeah. Okay. Yeah. Okay, so just as what I mentioned, I like to draw a figure to demonstrate what I mentioned just now. So if we have a positive charge, it will generally have an E field pointing from the charge. Okay. And then if we would like to draw closed surface or Gaussian surface, okay. So in such a way, for example, for this one, okay, so of course this is a circle. And then when we try to determine the direction of dA, okay, so this is actually the tangent line, and then the line should be perpendicular to the tangent line, and then dA should also be pointing outward. Okay, in such a way, dA is pointing upward at this point, and then dA is pointing to the right side at this point, dA is pointing downward at this point, and then dA is pointing to the left side at this point, something like this. Okay, so here we can simply see that, okay, so in this figure it's almost like integration of E dot dA, and we can see that E and dA are all pointing to the same direction, which means that in such a way we have actually E times dA cosine of 0 degree, and cosine of 0 degree is actually 1. Okay, so and here is the magnitude, so all the things are positive value, which means that all the things are positive, so that it turns out that the phi here will be, the net flux here will be positive. And if we have a negative charge here, so it will generate the E field pointing towards the charge. Okay, so similarly, we try to draw a circle as the Gaussian surface. Okay, so here when we would try to determine the dA, okay, actually it will be the same as the left hand side, dA. Okay, so the dA, the direction doesn't related to the charge to the E field. it only relates to the Gaussian surface itself. Okay, something like this. Okay, in such a way, when we would like to calculate phi equals integration of E dot dA, so it will be something like E times dA times cosine of 180 degree. Okay, all the E and dA are pointing to the opposite direction, so the theta will be 180 degree. So in such a way, this thing is -1. This is positive, this is positive. So we adding many negative numbers together, so it turns out to be a negative number. Okay, something like this. OK， 但实际上的话，就是它不一定是全部都是0度或180度了。但是如果能用手算的话，其实很大部分情况都是0度、180度。但偶尔还是有一些能算的，它是一个 theta 的角度，那就是后面的例子会算到的。那还有的话就是那个Gaussian surface，它是你自己定义的。看你怎么样有用，它不一定是一个球体，有可能是一个长方体，可以是一个圆柱形，可能是其他形状，后面就会用到。那就是说，你定义的那个形状对的话，那你就算得出来；你定义的不对的话，那就算不出来。但是通常的情况呢，它都是一些某程度上对称的，就是球体啊、圆柱体啊。或者是有些情况正方体也有可能的，但是这个就相对比较少见，通常都是球体的。Okay, so here we have a central problem. So here it says a Gaussian surface in the form of a cylinder of radius r immerses in a uniform electric field. Okay. So here, actually, we have an E field pointing to the right side. E field pointing to the right side, and actually it is uniform and pointing to the same direction, to the right side in this figure. Okay, which with the cylinder axis parallel to the field. Okay, so here we have a cylinder， 有一个圆柱体啦啊 ，and then 这个轴的话就是说。这个圆柱体嘛，所以它有两面是圆的嘛，那我们就把两个圆心连起来，那个线就是这个轴，就是 cylinder axis， 就是这个轴。Okay, what is flux phi of the electric field through this closed surface? Okay, so here for the cylinder, we can actually separate into 3 parts. Okay, so this is one part, this is another part, and then the side will be the third part. Okay, so we would like to calculate one by one. So this one is called A, the side is called B, and then this side is called C. Okay, so actually we would like to calculate the total flux. Or actually the net flux equals integration of the closed surface integral E dot dA. Okay, so and actually the integration is additive, so then we can actually separate into 3 parts, 1, 2, 3, and then we can write it as integration of E dot dA for the surface A. And then plus integration of E dot dA for the surface B, and then plus integration of E dot dA for the surface C. Okay. And after we separate the whole cylinder into 3 parts, every part are not closed anymore, so we don't draw a circle here. And actually, we can try to calculate these surface integral one by one. Okay, so first of all, integration of A E dot dA. Okay, considering this one, the E field is pointing to the right side, and then dA should be pointing outward and perpendicular to the surface. So dA point to the left side. In such a way, E and dA has an theta of 180 degree. Okay, so it is something like integration of E dA and then cosine of 180 degree. Okay, so this is actually -1. And also we know that E is uniform. E is uniform. So actually this thing is like integrating a constant, something like integrating 0 to 4, then 3 dx, something like this. This integration is easy to calculate, which is like 4 times 3, which is 12. Or you can just put this thing outside, which is like 3 times integration of dx 0 to 4, and this is actually 4, something like this. Similar for this, as much as E is uniform, we can just put it outside and then integrating for the surface, so which is just the area of this surface, which is like E times the area. We just simply call it A, which will be fine, and then -1, which will be negative dA. Okay, so before calculating the surface B, we calculate the C first. Okay, so we have integration of E dA for C, and actually we can see that the E field and dA for the surface C actually points to the same direction. So here we have cosine of 0 degree. So actually this is 1, which means that we have E times A. E times A. So finally, integration of E dot dA for surface B. Okay, so here we can have something like, you can see for surface B, for every point, the E field are pointing to the right side, and actually here you can see for this point, dA is pointing upward. Okay, so here, theta will be 90 degree, so cosine of 90 degree, is 0. 90 degrees 0. Okay, so E dot dA will be 0 for this point, and for other point, let's say for this point, actually is this dA is pointing out of the page. dA is pointing in this direction, and E is pointing to this direction. Okay, so this is still 90 degree, and if it is like at this point, okay, so in this case, this dA is pointing to this direction, and the E field is still pointing to the right side. So these two vectors also perpendicular to each other. Theta is still 90 degree. So in such a way, we have cosine of 90 degrees 0, which means that this E dot dA is E dA cosine of 90 degree. So this whole thing will be 0. Okay, so finally, you can just plug in this one, and this one into here. So here we have phi equals negative EA plus 0 plus EA, which will be a 0. Okay, so any questions? Everyone? Okay, so here we have another sample problem, which is a little bit more complicated. So, so you can see here it says a non-uniform electric field given by this expression E equals 3x I hat plus 4j, 4j hat. Okay, so actually this E field is not uniform. It is related to the coordinate， 就是跟坐标有关，跟那个 x 的位置有关。x 如果是0的话，就是在这个 yc 面上面的话，那这个 x 的 component 就是0。如果 x 等于1米的时候，那就是3乘以1；如果是3米的时候，3乘3，在这个 x 方向。Okay, P is the Gaussian cube as shown in the figure. E is in n over c and x is in meter. What is the electric flux through the right surface, left surface, and top surface? Okay, so we will try to calculate one by one. So the first one will be going through the right side, which means this one. This is the right side. Okay, so first of all, we would like to determine the direction of dA. Okay, and then so dA is perpendicular and pointing outward. So dA should be pointing to the right side. Okay, so in such a way, we would like to calculate integration of E dot dA. Okay. And then for the right side, okay, so we use a small r to represent right, okay. So in such a way, we would like to calculate E dot dA. So what is dA? dA is actually dA magnitude, the magnitude of dA, and then this is positive x-axis. Positive x-axis means it is actually I hat, right? Okay, so this is the magnitude, this is the direction. Okay, and actually the magnitude of the unit vector is 1, so it doesn't influence the total magnitude. So dA vector will be dA times I hat. Okay, so here we will be able to calculate integration of 3x I hat plus j hat, okay, and then dotted with dA I hat, okay. So sometimes I just draw an additional dot, but yeah, actually in the textbook it will be written as this without the dot here. Okay, for the right. Okay, so how to calculate the inner product between the unit vector? So it will be very, very simple. Actually, we would like to remember something like I hat dot I hat equals 1, j hat dot j hat equals 1, and then k hat dot k hat equals 1. Okay, and for any other I dot j, I dot j, I dot k, j dot I, and then j dot j, j dot k, and k dot I, k dot j. Okay, all of the other will be 0. 0, 0, 0, 0, 0, 0. Okay, so this is pretty much it. So in the Cartesian coordinate, when you like to dot any two of the unit vectors, okay, if if the dotted vector are the same, I dot I, j dot j, j dot k, then it will be 1. Otherwise, the dot product will be 0. So it is really simple. So here we would like to calculate this. Okay, dA dotted with the previous thing. So we would like to distribute this one to here and distribute. 就是分配率嘛，乘法分配率嘛。那 dot product 就是一个点积，所以它还是一个乘法，所以就是按照乘法的规则去算。Okay, so here I dot I will be 1. So we have integration of R and then 3x dA. And then for the second term, j hat dot I hat will be 0. So we don't have anything remain. Okay, so here we have this stuff. And actually for the right surface, x is actually equal to 3. X is actually equal to 3. So here we have x equals 3, which means we have an integration of R 9 dA. Okay, so this is a constant. We can just put it out like something like this. And this is nothing but the area of this y surface. And you can see this is 1 meter, 3 meter, which means this is 2 meter. 2 meter long cube. Okay, this is a cube, so every side are 2 meters, which means the surface area will be 2 times 2, which is 4. So this is 9 times 4, which is 36 nm squared over c. Okay, so this is the first answer. Yeah, 没问题。So let's go through the second and the third one. Okay, so here we would like to calculate the electric flux for the left phase. So which means that it is for this one. Okay, so in this case we have dA onto the left side, which means this is actually dA times negative I hat, or we can write it as negative dA I hat, something like this. Okay, so similarly, we can find the surface integral. This is for the left surface, so we use an L. Okay, E dot dA. Okay, so here we have integration of L, and then we have 3x I hat plus 4j dotted with negative dA I hat. Okay, so similarly, I hat dot I hat will be 1, j hat dot I hat will be 0. So we have an integration of L negative 3x dA. And actually for this left surface, x is actually equal to 1. So here this x equals 1, so we have integration of negative 3 dA L. So it is nothing but 3, negative 3 times 4, which is negative 12 nm squared over c. Okay, so a little bit different is that this x is 1, this x is 1 for the left surface. And then for the final one, the top face is actually this one. Top face. So here for the top face, dA is pointing upward. So we can write it as dA times, this is y-axis, so it's j hat. Okay, so similarly we can calculate integration of E dot dA for the top surface. So here we have integration of for the T surface, and then we have 3x I hat plus 4j hat dotted with dA j hat. Okay, similarly we can just distribute this thing to here and here. So for the first term, I dot j will be 0. So the first term vanish. And then for the second term, j hat dot j hat will be 1. So in this case, we have integration for the t surface, and then we have 4dA. Okay, this one we have, we have a 0 for I dot j hat. Okay, so here we have 4 times the area is still 4, which is 16 nm squared over c. Okay, so let's have a 10 minutes.